So, good morning, students. Today we are going to learn about trajectory planning. This is an important aspect in with respect to the robo because unless otherwise we have proper plans on making trajectories, it is not possible for us to provide the required motions for the tool or end effector in a robo. So, this is what is actually the major aspect associated with the robotics is actually moving the robotic arm from one location to the another because robo arm is going to be moved for satisfying different requirements. Based on the applications, the requirement is going to change. So when you are having a particular movement, that movement might be possible for us to attain it in multiple ways. Say for example, you have 2 points A and B. You are trying to move them between points A and B. So that movement from between A and B, there may be thousands of possibilities, but we have to select the appropriate one. Only then we will be able to complete the task in an effective manner. So for which the trajectory need to be planned properly or the path it is going to follow had to be planned properly. For which we are going to take the support of kinematics. And of course, kinematics, the term whatever whenever you have come across, we are going to take into account the mathematical models, which is going to give the description of the tool position and orientation within the work envelope. Say, for example, if you try to consider a robo, there is going to be a work volume, which means that your robo can be used only within that particular volume. There is going to be a lot of limitation. So, which we have introduced in the first units regarding that. So, taking into that account, one aspect is moving the robo arm in a particular path as well as keeping the particular tool in a particular orientation. Okay, you can try to give a physical movement for your hand while picking up an object, how the orientation is changing for your arm and the wrist. And say, for example, you have picked a pen and you have tried to use that pen to write some content on a paper, how exactly the variations are happening with respect to the orientation and what are the forces with which you are trying to hold the pen, all that you will be able to catch up. So, whenever there is a movement from one point to the other, there will be generally some series of points or a third point through which the movement is going to proceed. So for which you are going to have the different geometries, rather different locations. So in order to get an idea on that, this particular figure is being showed in slide number 4 is going to be helpful for us. We are trying to move from A to C through the point B. You can see the orientation. Say there is an end tool which has been represented by a line. How exactly it is varying. When it was in A, at position A, it is almost all in vertical position. When it has been moved to B, it has been made inclined, and when it has been further moved to C, the inclination was further improved. So this is how the orientation matters a lot. So this is the trajectory. Maybe the path whatever has been referred to passing through is actually the trajectory. If you want me to quantify the difference between path and the trajectory, path is going to specify the sequential positions through which the robo end effector is going to move. Trajectory, when it is coming, it is going, no doubt it is going to follow the path, but it is going to attach a timestamp. Maybe at position A, what is the time? At position B, in order to reach position B, what is the time? And maybe to reach position C, what is the time? So time representation is also going to be there in the trajectory. So that is why this is actually the trajectory is actually represents both spatial and temporals when a motion is actually happening. Once it is there, there are two possibilities through which we will be able to represent that information. Maybe with the support of giant space or with the support of Cartesian space. As I said, in trajectory, there is going to be time history of what and what position it's going to take into account, velocity, acceleration for each and every degree of freedom. because you are going to have n, if you have n joints in a robo, that means that there are going to be n degrees of freedom. N joints are going to be there automatically. So at each and every joint, whatever is happening, all that is going to be recorded. So trajectory specifies all that. So same thing has been represented here, whereas the configuration has been showed in the diagram is more or less trying to give us an idea on the Cartesian. Say there is a movement from A to B, and you can see so many subdivisions. There are so many subdivisions. They are all intermittent locations through which your robo is going to, M defector is going to pass through. So when you want to attain this, you need to have the Cartesian space. So anyway, unless otherwise you have path and trajectory planning, it's not possible for you to move from one location to the other in a controlled manner, because what you are aiming at is actually there should be some controlled motion for your end effector. So that if you want to do, there should be trajectory information, perfect information on the trajectory. So if you want to have proper planning through trajectory, you have to take the support of two aspects, like kinematic aspects as well as dynamic aspects. Okay, so kinematic aspects bothers about the links, lengths, motions, and everything. Dynamic aspects is going to bother about the forces, torques that are going to act at each and every joint. So unless otherwise you have precise information on this, it may not be possible for you to devise a smooth motion for your robo. So the same information has been kept in a described manner. So one is actually, if you want to have a proper plan, you need to have path specification, and you should also have perfect idea on the path constraints along with the dynamic constraints. This particular slide, whatever I'm projecting, showing some text in the red color. So under that particular side heading, those red colored things are important. Let's say under path specification, generating trajectory points. So once you have them, there should be a polynomial function using which you are going to analytically link up them. Then path constraints, when you try to refer derivatives of velocities and acceleration. These are important to take care of the jerk, whatever might come across. Once you have jerk in a considerable quantity, then the movement is not going to be smooth. It's going to be oscillatory. So that is how the things are. Then coming to the dynamic constraints, torques that are all happening at the joints and forces, there should be proper control. Say for example, so you are trying to move a particular paper. In order to move a paper which is actually with lower weight, you doesn't require much of force, and you might not experience much of torque. Whereas if you are trying to handle a heavier object, automatically forces what all you are going to control, and the torques that are going to be experienced, that's going to be much more. So this is how these aspects are very important. Keeping all these aspects in mind, only then you'll be able to optimize the path. Same information you'll be able to understand from this. Say this particular flow diagram or block diagram is going to give us an idea on the parameters on which the path planning is depending on, and what are all the parameters that are all coming as an output with a proper path planning. See, you can see dynamic constraints, that is what we have said, joint torques and forces. Then coordinate data might be in joint representation or Cartesian coordinate representation, and the path specification, there should be a polynomial analytical function that is going to connect all the points through which your path you are planning at. So all those things are going to form a basis for your path planning. Only because of that, you will get the exact positions, exact velocities, exact accelerations, and the coordinates values, and the proper orientation. Then anyway, output is actually, we have already showed in the block diagram. That's what, see, giant variable space vectors like velocity, acceleration, and generated coordinates gives the insight into the path outputs for the control of the robot. So all the data is going to give us a proper insight on the coordinates, so that is going to give us how exactly the velocities are and how exactly the accelerations are, and only through them we'll be able to gauge the proper output. So let us continue our discussion. So the major constraints that are supposed to be taken into account at the time of path planning are obstacles that might come in its way, and the path. Say there may be some restrictions with respect to the path that we need to adopt. And of course, this we have already seen. And there are various ways and means using which the path planning strategies can be adopted. They have been listed here. Few of them are on offline, few of them are on online, and they will also take into account the collision that might happen, and it should ensure that the collisions should be avoided, and some methods that you might adopt might contribute towards the collision, and all those things you should evaluate them and validate them properly. And the points that are supposed to be kept in mind, like grasping and releasing objects, moving from place to place, maybe all these items being listed out here, they're all being listed out keeping in view of a particular process, a simple process. When you try to consider that is being executed with the support of a robo, all these operations are going to be there, like moving an object, placing an object, picking an object, and forces, torques, and data that is all related to the tools, whatever has been. So these are all the points that are all going to be kept in mind. And of course, all the salient connecting points have been listed under the various title called essential performances and mechanical constraints, general requirements, evaluation criteria based on control method, and criteria for implementation. So all these things are actually they all these things can be realized once you try to visualize a simple example. So keeping a simple example in mind, a pick and placement of place operation itself, all these points have been figured out. See, we can again understand the trajectory generation process looking at this particular flow chart, like path planning, first phase, second phase, trajectory plan, then the third phase is going to bother about robo control. So robo controller is going to have a combination of acting and sensing. So it is going to take the information through sensors, because it has to know and conclude to what extent the targets have been reached, completed. Based on that, the feedback had to be generated. Based on that, the corrective measures are going to be taken. And of course, few examples like arc welding and specific path have been shown. So those things demands continuous process, whereas pick and place will be demanding PTP motion. So from here we are able to conclude that there are two types of motions. Requirements is actually different for various requirements. If you are bothering about a pick and place alone, so that's going to look for PTP. If you are bothering about arc welding or something like that, it needs continuous motion. That's why continuous path is actually required. And anyway, altogether the total moments, the total content out of this is actually bothering about the via points. So when you have considered via points that may demand us to go through straight line path or circular path, or maybe we may have to adopt through higher order interpolation. So whatever you do, it should it with the control what the mechanism whatever you take up and apply, that should avoid the jerk to the possible extent. So once you avoid this particular jerk, there is going to be smooth motion. Okay, so there will be no shaky across the movement of your robo and effector, and oscillations also will not be there. So you should ensure that such a kind of measures are supposed to be taken. And of course, this is all depends on the velocities and accelerations also, and that's why planning is actually required at the trajectory level and at the path that's being adopted level. All those things matters a lot over here. So now coming to the scheme of path generation. So as you all know, there are two schemes: joint space scheme and Cartesian space scheme. So that you can understand from this. like see, initialization of the time, beginning of control loop, time increment, then after that computation of joint positions, then the final time step. If that is satisfied, fine, and then it goes out. Otherwise, it will come back and it starts with the fresh time. So until the total time has been completed, this flow chart is going to continue. Okay. So anyway, similar kind of loop is actually being applied even for Cartesian space. So when you try to look at this particular flow chart, whether the scheme is coming under giant space or the scheme is coming under Cartesian space, the flow diagram is more or less same. Okay, so the only thing is the parameters you are trying to evaluate, say time increment, and then the computation of giant angles are coming here. Then in this case, time increment, specification of hand position and orientation is coming here. After that, the computation of giant solution is actually being attained. So this is how, with reference to this particular flow diagram itself, we are able to conclude that the Cartesian space method is actually computationally intensive. If you try to give a comparison between giant space and Cartesian, so this is bothering about one particular method. You can see you are having a six-axis degree robo, six-axis robo, and you are supposed to move the robo from point A to point B. Okay, so when you consider this through giant values, so you are trying to bother about giant space, we will not be able to predict how exactly it is going to travel between point A and to B. Okay, so four different ways have been shown. It might follow one out of these four or something else. So motion between them is unpredictable. Whereas if you try to refer the other method, Cartesian, when you are planning to move from A to B, you can see there are multiple discrete locations, and through all those points, this end effector is going to travel. So when it is traveling, all the joint angles are also varying, and the variation is not uniform at all joints. It is different. Okay, so this is what we are able to understand from here. This is again is going to give us a scope to understand why this is computational intensive, because it is trying to satisfy almost all the points through which it is trying to navigate. Both the schemes have got their own advantages and disadvantages. Say for giant space advantage, when you try to refer, we are trying to have a control directly, whereas it is not that easy to determine the locations of giants and links when the motions are happening. And as you have seen in the earlier slide with respect to the pictures, since we don't have control between the motions between the motion between the points A and B, it is not possible for us to avoid obstacle. So though even if it is possible, it is a bit difficult. So because of the unpredicted motion between the points, we are not in a position to satisfy the requirements of accuracy. Less accurate, though it is actually capable of satisfying some level of accuracy, but still, when it has been compared with Cartesian, it is actually a little less. That doesn't mean that Cartesian space is actually having so many advantages. So, though it has got computational intensive because of that large control, large controls are there, because of that control intervals should be more and more. And since you are trying to have an idea on the hand coordinates, and that has to be mapped into the giant space many times, because of that, anyway, as an advantage obstacles, it is easy for you to avoid during motion whatever has we come across. Maybe some of the disadvantages whatever we have come across in giant space have been overcome here, and some of the disadvantages whatever have been experienced in giant space have been overcome here. So that's why we cannot avoid both. So each and every representation has got its own usage at multiple different locations. Now, coming to this, say Cartesian, see, there are two situations wherein it might fail. Say, We have a point at one end of the robo, and there is another point at the other end of the robo. In between, its base would be coming. How to go about it? It would have been instructed to travel a linear path, but in between there is a base which is coming in its trajectory. Now, if you look at this, there are 5 points have been shown. For 3 points, it is with some other configuration, and for the remaining 2 points to satisfy all the joint variables are varying. So it is not that easy to change suddenly the total joint angles. So this is again another difficulty that might come across in Cartesian. And same points have been listed out in the name of characteristics, say desired locations and the computational intensive whatever has been discussed till now have been represented over here. And there are 2 points that has to be covered under this: normalized and not normalized. In the normalized and non-normalized, what is the difference? Say for example, there are two joint angles. Say joint angle alpha, it has to be range varied from 20 to 40. Say beta had to be range varied from 30 to 80. Say if the maximum angle with which it can be traveled is 10, if it is, then alpha angle is going to be completed in 2 steps, whereas beta is going to take 5 steps. Means alpha related joint or in the link is going to complete and wait, it's going to stop, whereas the other link which is going to cover which is covering beta angle, that is going to vary from 30 to 80, it is continuing its motion in spite of link 1 has stopped. Because of that there is no uniform movement. So because of that reason, our travel might not be so smooth. So there is a possibility of getting some coming across some jerk. Whereas in the normalized, the total time the alpha is going to be moved from 20 to 40, as well as beta is being varied from 30 to 80 is going to be managed by altering the velocity with which the link 1 is going to be moved and the velocity with which the link 2 is going to be moved. No doubt link 2 is going to be moved with highest possible velocity. Link 2 is going to be altered and reduced with a reduced speed it is going to. We are able to get some uniform motion between the points. That is advantage in this. Same thing has been described in theory. And the other two sketches say now the first one is actually trying to give you a normalized one, whereas we will not be able to proceed and implement that in the program. The major reason is if you want to have uniform variations with respect to the velocity and all, at the starting and end points also, acceleration should be more. So pickup should be more and deceleration also should be more at the end, which is not possible. That's why slow pickup in the beginning and slowly stopping up in the end means deceleration in the end should be adopted. By adopting them, once again, the total motion was regulated. See, both the angles are varying continuously. So this particular technique is here, but still the aspects of velocity and acceleration and decelerations have been kept in mind so that they wanted to reduce the jerks that might come across when you want to maintain the same speeds, velocities, and acceleration throughout its travel. All that is not possible. And of course, in slide number 30, we'll be able to see that x equal to half at square and v equal to at. So these two are the principles what you would have come across at intermediate level. So bear it in mind that whatever the principles we have learned, all those things are going to be helpful for us either way in the other way. One way or the other way. Say robotics is an advanced area wherein the principles whatever we have learned in physics are much more helpful for us in order to proceed in a systematic way, scientific way. Okay. So with this, I would like to stop the presentation. There are much more aspects that can be covered, but for the time being, I would like to stop at this level. Thank you.